All right, let's try an example of this. So, of course, what's almost always my first step with these types of integrals? Yeah, get my parameterization. So I want this to be the line segment from -5, -3 to 0, 2. You could do the official R of t blah blah crap. And then, but what's the line that goes between those 2 points? What's the equation of the line? What's nice about 0, 2? It's the freaking y-intercept. So what's the slope? 1. Change in y's, change in x's. The slope is 1 and the y-intercept is 2. Why would you need help with this? Even if the y-intercept wasn't that easy, who cares? You should be able to make the equation line very quickly. You don't have to go back. I mean, it's nice to just always have that R of t and just throw shit in there, but now I know what to make t. If you do it the other way, neither one of them is just t. It's just nicer this way. I want something to just be t. That's nice. Right? I can hold on to that. Well, what am I going to let be t here? It doesn't really matter. But the way I've written it, x is t, and then y is? That's crazy. So then what's dx? dt. And what's dy? dt. Well, and do you see why I need all that stuff? Of course I do, right? Because I want to replace everything that's in there currently with its parametricized version, right? All the y's, x's, dy's, dx's. What's t going from to? X is t. Yes. If they would have said from 0, 2 to -5, -3, I would have had to do from 0 to -5. I have to go the direction that it wants me to go. And why does that make sense for later? Well, if I go this way versus this way in a vector field, that can completely change. I could be going with it or against it. Oh shit, so direction matters. Big time. Direction matters through all of chapter 16. Holy shit. So it's going from this point to that point. So t is going from -5 to 0. So if it was going the other way, I couldn't really write it like that too well. But oh well. So I know it's going to be from -5 to 0. Y squared is t plus 2 squared. Dx was dt. Plus, what's x? T. And what's dy? dt. So let me just put a dt at the end here. Yeah. Isn't that nice? I mean, it's kind of like a little, like, we're sorry for the last chapter. Here's some nice stuff for you for a little while. And then it quickly becomes, oh, here's shit. Here it comes again. So enjoy this, the first 3 chapters, the first 3 sections of this. Because then yeah, sure. So then -5 to 0. What do you get? T squared plus 4t plus t is t squared plus 5t plus 4. And then that's a polynomial, so who cares? Cool. And now if you look at, this is an example I think the book does. And they do it, it's on page 1119. And it's not like longer or anything, but you can imagine it wouldn't take a lot to make a more difficult problem. They do this business because they use this business, right? Which works. It works. There's an infinite ways to do the parameterization, so yay. But then everything's just a little bit grosser than it really had to be. It depends on your take. It's just a little bit worse than it had to be. And it only works for lines anyway, so I can get the equation of line. If you can't, oh, wow. Okay. And they got negative 5, 6. Is that what we get here? We get t cubed over 3 plus 5t squared over 2 plus 4t from negative 5 to 0. Look at 0 when 0, then it's going to be minus negative 120. So 125 over 3 minus 125 over 2 plus 20. So this is 2/6 of 125 minus 3/6 of 125 is 1/6 of 125. And then 20 minus 1/6 of 125, it does work out, believe it or not. Yeah, because 6 times 20, 120 minus 125 is negative 5, 6, which is what they got. Ooh. When you get a repeated number like that with different values on the bottom, just look at it like that. This is 2/6 of 125. That is 3/6 of 125. So it's negative 1/6 of 125. Who cares? All right. So what about this one here? You guys try this one here. Same thing. Same integral. But now I want it done. C is the arc of the covenant. No, this is the arc of the parabola. X equals 4 minus y squared. I think it's the same points, right? Yeah. So notice something interesting here. It's the exact same starting and ending point as that last problem, except now I'm taking a different path to get there. So living in San Diego, we're all very aware of different paths to get home. If you're not, you're lucky, I guess. But you look at Google Maps, you're like, well, shit. Let's try this way. So there's multiple ways to get between a beginning and end point. But does that necessarily mean, since I started at the same place and ended the same place, am I going to get the same answer here? Hopefully you realize, hell no. We would if the field I was working under, we're not even to the point where it's fields yet, was conservative. That's the trick. So that's the little shortcut we do. Once we're working with fields, if it's a conservative vector field, then it's just like what we do with integrals in 180. How do we evaluate integrals in 180? We do big ass F evaluated at the end minus big ass F evaluated at the beginning. Does it really matter what it is in the middle? No. Because if its antiderivative exists, then it works. So a conservative vector field basically says that. It says an antiderivative exists. If you look back at what that was. All right, so do that. Guys. It can't be the same because we're using a different path. That was a straight line path. This is now the arc of the parabola. Sounds like a much worse thing for Indiana Jones Collective. About the arc of the parabola.
Or y equals square root
Ah, there it is. All right. So hopefully, would you guys use? Yeah. Yeah, y equals t. You didn't have to. You could use y equals radical t if you want to. No, you're not wrong, man. I mean, it's fine. It's just I'd rather not, because then I have to take derivatives of it. Do you see what I'm saying? I'd rather keep my my t stuff simple, because their derivatives are going to become a part of the integral I have to do.
So is y always going to be t or x? When is it not going to be t?
That's what I always try to do. Sometimes it makes more sense. If I'm on some circular path and I want x to be sine, y to be cosine, nothing's just t. Do you see what I'm saying? If I try to force something to be t, I get this disgusting plus or minus square root bullshit when I'm on a circular path. So there are certain paths that functions besides just t are nicer to use. But most of the time, for any polynomial kind of definition, and there are a lot of root definition where I'm going to use something's going to be t and the other's going to be built off of that. Yeah. Okay. I like it. Let's see, so x is 4 minus t squared, so dx is, negative 2t dt, dy is dt. So then you get, and what's t going from to? Yeah, so y is t, so t must be going from negative 3 to 2. So that makes that step easier too, right? So from negative 3 to 2, y squared is t squared, dx is negative 2t dt plus x dy is dt. So I just collected my dt's there at the end. Yeah, I know. So yeah, I feel like I'm done. Yes. So here's the y squared. Here's the dx. and the dt piece I just put back here. And then here's the x, and the dy was the dt. I like it. Because remember, when you write it like this, there's an understood integral here. We just don't write it twice. But when I bring the dt stuff in there, that could just come to the end. It's become one big integral again, because now it's all dt. So you got to get a little used to that. And like I said, I mean, now it's just, what do you get here? Negative 2t cubed. So when you integrate that, you get negative t 4 over 2 plus 4t minus t cubed over 3 from negative 3 to 2, and you throw all that shit in there. See, this is right out of the example. So they get 40 and 5/6. Now, which would you say is the shorter? Which would you say is the shorter path between the 2 points? Probably just as the crow flies, right? So it seems that the path I'm taking for this guy, the path I took seemed to line up with things better. So this is sort of, I'm thinking ahead to when we do vector fields. If I'm lining up with the vector field, if I line up with it the whole time, I'm pointing, the path I'm taking is in the same direction as the vector field, my integral answer should be positive. Should be maybe big positive if I'm picking up a lot. If I go against it the whole way, my answer is going to be negative. If it's partial against and partial for, it could be 0 or whatever. Do you guys get a feel for that idea? That's what we're going towards. So this is a big time indication that the path is path dependent most of the time, unless the vector field I'm working across is conservative. Then it's path independent. It's kind of cool. I like it. I like it. Let's see. What's the one last little thing I want to do? Let me see if I can sneak this in here. What time is it? Not too bad. Oh, good. We got time. So we got that? Say erase it. And by the way, if you're, while I'm thinking about it, I'm flying out to Minneapolis this afternoon in about 3 hours. So,
Yeah. There's traffic?
Yes.
I live right next to the airport. So I'm not going to be here tomorrow, so I'm trying to say. So if you want to come by and see me tomorrow, I'm not going to be there. So, yeah. Let's talk about this. I keep talking about line integrals along vector fields. So I want this to make sense. The same way that a fourth dimension could either be a fourth physical dimension, or it could be a value of density at a point. You with me? It would be a fourth required parameter, so it would be a fourth dimension. The way that we looked at line integrals so far is only one way to do it, as a curtain underneath the surface. But now we're going to look at it as a line integral through a vector field, right? So we're going to have to do vector-related stuff to this. Let me see if this makes sense. If I have a defined vector field and I have some path through it, so some vector field, and then I have a path, and here's C through this, right? You guys with me? And of course, C is going to be R of T. I'm going to come up with some parametricized version of that. So here's what we were talking about earlier. Here's where that all comes back to help us out. If my R of T is perpendicular to the vector field at a point, that's going to contribute how much to the integral? Nothing. If it's lined up perfectly, it's going to contribute the whole thing to the integral, right? So if I'm askew a little bit, I'm not perpendicular, I'm at like maybe 37 degrees, what operation do you think is going to come back to help us?
Dot product.
Dot product, which involves cosine length. So dot product, right? That's what helps us in any dimension, right? Dot product helps us in any dimension. So what this is going to end up being, so this is going to be some a path through a defined vector field. It could be any kind of vector field. It doesn't have to be conservative. If it's conservative, the math is much nicer. Much nicer, right? By the way, this is page 1123. So F has got to be continuous. And C has got to be smooth again, of course. This kind of makes sense because this is all built on breaking it down into small parts that eventually becomes linear. And if it's not smooth, you can't. That's what it means. You can't do that somewhere, at least at one point. Blah 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 blah. So you end up with this. Should hopefully make sense across that curve. So this is exactly what we would expect based on what we just said. I'm going to take the dot product between my motion through it and the vector field itself. So that I can rewrite this in a much nicer form. I love the way they do this. Here at the end you have this weird thing. I don't know if you can go back and remember dealing with all that. It was in the same area as the beautiful T and B reference frame and all that, and the osculating plane and all kind of weird shit. And we dealt with the relationship between T and R and S and all that kind of stuff. Okay, I like it. So that kind of plays into the math behind this. And then the middle integral is the one that's the most useful. So I like that they have this is the same as this, is the same as that, and this is the one we use most of the time. So let me write this all the way out. Same way they got it. I like it. So see if we can sneak in here an example. Let me see if I did one already. Oh, I don't want that. No, so I can do one right now. Here, let's do this. There we go, there. See if they give a, the picture isn't that illuminating. So sometimes this is nice, sometimes this is the one that's most computationally useful. So can you identify what it is that we need to figure out right now? We need to figure out what that. We need to figure out what R of t is. Well, that's given to us, right? Right. The x, y, z piece is given to us. So that's a nice one to start with. And then we need to figure out what R prime of t is. We need to figure out what f evaluated at R of t is, right? Do you guys see what's happening? Mm-hmm. All right. So just to make sure, what is R of t? You put it in a little more standard format. R of t is t squared, t cubed. So what's R prime of t?
1, 2t.
Yeah, 1, 2t, 3t squared. Where am I at? Two of those. Oh, yeah, okay. So then I need what f is evaluated at R of t. So, I mean, f then will be, what's x, what's y?
So t cubed.
Yeah, so that'll be t cubed, y, z, t to the fifth, and then zx to the fourth. I like it. So the work here is different because I don't have a surface over a line. I have a line going through this field. So that's the dot product makes my work different. I've got to take the dot product because I want to know how much my path lines up with what the field itself is doing. So it's not going to be the same kind of work. Not always. So here, what's the last piece? I've got basically everything I need. This is f of r of t. Yeah, now I just need the dot product between r prime and f of r of t. Right? So then you get the integral from 0 to 1. The dot product is they're right on top of each other. That's nice, what I did for myself. So what's the dot product between these two things, right? These two things?
T cubed.
Yeah, t cubed plus 2t6 plus 3t 6. That's nice. Some like terms. dt. And again, that's just some polynomial. I feel like I'm done. Let's see if they got the right answer. Yay, they did. Let me see if I want to do that yet. No. I feel like that's enough for today. What do you think? We did plenty. We're almost, we'll know what happens for the next test come this Monday. We'll know what's going to happen. So just to remind you guys, the next test has been pushed back. It's not next Wednesday. It's the following Monday, whatever date that is.